In order to really understand how to model the problem of the firm and the technologies of the firm, we need to introduce or make use of a tiny bit of multivariable calculus. In particular, the need to work, and it's the only thing that we will need, with something called partial derivatives. Now, if you are familiar with these concepts from your previous studies, as I'm sure many of you are, skip this video. There is nothing here for you but extreme boredom. On the other hand, if you have never taken multivariable calculus, partial derivatives sound like an exotic, interesting concept for you, or if you want a refresher, keep watching. Consider a function of two variables, x and y. The symbol, this funny looking delta over dx, we're going to call this the partial derivative of f with respect to x. And we're going to call this symbol the partial derivative of f with respect to y. And the partial derivative of f with respect to x is basically the marginal change, the f induced by a marginal change, dx, importantly, while holding y constant. Similarly, the partial of f with respect to y is the marginal change, the f induced by a marginal change dy, and again, importantly, with x constant. Now, you can think, for practical purposes, of the partial of f with respect to x basically as the derivative with respect to x of a function of one variable that is x with y fixed. So you want to take this partial derivative at a point xy, think of constructing a function that has y fixed. Now you get a function only of x, and you just take the derivative with respect to x. And similarly, the partial of f with respect to y, think of it as defining a function fxy with x fixed, and you just take the derivative with respect to y. Notice what this means in practice. It means that when you're taking the partial derivative of f with respect to x, you hold y as constant, and when you take the partial of f with respect to y, you hold x as constant. You treat it as a constant. Let me show you what this means for the mechanics of how to take these partial derivatives, which is actually extremely simple. So suppose, for the sake of a concrete example, that we have the function xy is equal to a x to the alpha, y to the beta, when alpha and beta are some constants greater than 0. Now, what is the partial of f with respect to x? What we're going to do is we're going to take the derivative of this function with respect to x, treating y as if it were a constant, just as a is. So what do we get? A, y, b, beta, those are the constants, times alpha, x to the alpha minus 1. That should be straightforward. Now, what about taking the derivative of f with respect to y? We do the same thing, except that now we treat x as a constant. So let's write first the constants, ax to the alpha, and then we take the derivative of this, which is going to be beta y to the beta minus 1. Please take this example as reassurance that the mechanics of computing these derivatives, these partial derivatives, is straightforward. It's just a trivial generalization of what you know from univariate calculus. Let me give you a graphical depiction of what these partial derivatives mean, so you see that it's actually a straightforward generalization of what you know from univariate calculus. So I'm going to do on the left-hand side the partial of f with respect to x, and I'm going to illustrate on the right-hand side the partial of f with respect to y. So let's think about what this means. I'm going to draw the three-dimensional axis. So you have x you have y, x increases this way, y increases this way, and in this z-axis we plot the value of the function. Now, think of fixing the value of y, let's say there, and let me draw a cut, kind of the plane for your illustration, just for illustration purposes, that passes through there. You get the idea. Now what we can do is we can plot what the function is within that plane. So for example, let's say it looks something like this. So that would be what f of x comma y looks, given that y is called a y bar. So as you vary x, how does the function looks like? Now, what is the partial derivative of f with respect to x? Let's say at any point x. So let's say we want to compute it at a point like this. This is a point x. This is the value of the function. So the partial derivative is going to be the slope of the function here. Slope is the partial of f with respect to x. So it's a slope, just as before, of this function, of how this two-dimensional function is changing when you move in the x dimension. Now let's do a similar thing, but for the partial derivative of f with respect to y. So again, we can draw the axis, x and y. But now what we're going to want to do is hold x constant, let's say at x bar. Now let me draw the plane that kind of goes through there. This is the plane that goes through there. And as before, what we can do is draw the function, how the function cuts that plane, how the function changes within that plane. So let's say it changes something like this. So that would be the function of x bar comma y. And let's say that we want to take the derivative at a particular point y, let's say there. So we can go there. The value of the function is shown in that point. What is the partial of f with respect to y? Is basically the slope of the tangent within the plane that passes through that point. So that slope is the partial of f with respect to y.